The square velocity is the minimum velocity required for an object of any mass to be launched from surface of a planet to a point at which potential is zero. Oh, potential is infinity. Sorry. My bad. Zero. Okay. So it is basically launched to the point at potential such that the object does not return back. So each planet has a constant value for this, and it will be like that forever. So let me just tell you how we derivate this. And obviously, this derivation is also there, which is pretty standard. So no worries. Okay. So let's look at the derivation first.
Richard, could you move up for a second?
Oh, yeah, sure.
Just a
Sorry.
minute. Just a minute.
Okay. You can do that.
Sir, I think I should be making a joke when it comes to the object does not return back to the planet.
Yes, you could throw your brother out if you
Oh
want.
my god, brother.
Yeah, obviously. So
Yes,
we are
Ben,
doing
thank you.
we'll try to find out at what velocity you should throw him. So then yeah. So the first is the velocity. You need to, basically do this. And this is the derivation, by the way. So what you're gonna do? Yeah. Okay. So it says that the mass of the spherical planet may be assumed to be a point of mass, stone traveling at speed v in a circular orbit, or show that the speed is given by this. Oh, first of all, let me just this. I want to do the derivation separately because this question has a different idea about it. Wait a second, that's a different derivation. So we can move this point here. Let's do the derivation and then we'll do the question. So first of all, we should understand that the work done is equal to the change in potential times the mass. And we're talking about the work that is done when between, moving something between the surface to infinity. That's what you're looking for. Okay. Now, so to do that, to throw something out of the field, you need to initially provide a kinetic energy. And kinetic energy is given by half mv squared, and we're looking at this velocity v scale, where the change of we can write this and this. Now, if you see, the mass why it's written that the object of any mass, because the mass is irrelevant, just cancels out, which means then that you could do v square escape equals to 2 times like this. Okay. And then you can take root of this, and the escape velocity would be 2 times this root. Now, what you need to remember is that this change in potential is basically between infinity and the surface, would be the potential at infinity minus the potential at the surface. So infinity potential is always 0, and the surface has minus gm over the radius of the planet, like that. Okay. Obviously, then it's going to be gm over r. Now, what you want to do is you can replace it there, and when you replace it, it's going to be v escape equals to 2 gm over r. Root will give you um, the speed of the escape velocity at any planet. For instance, if we talk about Earth, so I know Earth's radius and everything by heart for some reason. I don't know. So 2 times we're going to do 6.67 times 10 raised to power minus 11. Earth's mass is 6.02 times 10 raised to power 24 kilograms. And the radius of Earth is 6.4 times 10 raised to power 6. So basically, for Earth, I'm just giving you a small example. So for Earth, the escape velocity is 1.12 times 10 raised to power 1, 2, 3, 4 meters per second. That is the speed you should throw something. Anything, if you throw it at this speed, it will never return back to Earth. Understood?
Lovely. Thank you for the information. We'll use later.
Yes, please. But if you realize this, okay, if you realize this value, just give you this value is huge, because if you convert to because we understand miles or kilometers per hour better than meters per second. So if you want to convert this into kilometers, you got to divide this value by basically 1,000 to convert it into kilometers per second, and then multiply this by 3,600 to convert it into kilometers per hour, which means you need 40,000 kilometer per hour, which is beyond the sound barrier like 10 times. Oh, more than 10, 12 times. Understood? So that's that much. You can't read that speed. I'm sorry on Earth. Anyway, going for the first question. Have you guys written this? Should I go on? If you have any questions, please let me know.
What is the value you got for the kilometers per hour? I wrote 11.2 kilometers down. What is that value?
That is 11 meters in kilometer per hour, 1,000 kilometers per
Sir,
hour.
your voice is breaking, sir.
Sir, you're lagging.
Okay, wait. Let me change the internet, please. My internet, I don't know, for a few days it's gone really bad. Wait a second.
Now yes, now it's okay.
It's okay? All right. Okay. Never mind. So it's 40,000
No, it's
40,000
breaking again,
kilometers
sir.
per hour if you want to. Okay.
Thank you, sir. I wrote it down.
I think it will be fine now, I believe. You guys can hear me now?
Yes, sir. Yeah.
Okay, good. Now going to the next one. In this one, it says the mass m of spherical planet is about this one. And if you look at the question, basically it says that um, show that the speed given by. Now, this speed is basically the vector speed. This question is not related to this. I don't know why this is posted here. Let me check what happened to this is not escape velocity question. Why is it here though? This is a classic question from kinetic energy. Okay. All right, leave this. This question will come back again. And the same. This is the same. And this is the same. Okay. Yeah. So we're going to start from basically this question. So in this question, it says gravitational potential at a point. So we're going to write it is the work done per unit mass in moving. All right. This mass from infinity to a point. All right. Within the field or to the point within the field, whatever. Now it says moon considered to be isolated and it has a radius and it is mass is this and concentrated. A rock of mass 0.5 kg is situated on the surface of moon. Show that the change in gravitational potential energy of rock moving from moon surface to infinity is this. Okay. First of all, what you're going to do is we know that it says the gravitational potential, the mass is given and this is given. Okay. So the change in gravitational potential is given by gm over r. So g is 6.67 times 10 raised to minus 11. Why I have taken it positive, I'll just again tell you, because it's talking about infinity to this. So potential at infinity minus potential at moon. So we're doing this. So this is 0 minus gm upon r. Okay, like that. And now G is 6.67 times 10 raised to minus 11. The mass of moon is 7.35 times 10 raised to power 22, divided by the radius of moon is 1.74 times 10 raised to power. Now you need to convert this to 10 power 6 like this, okay? So then if you help me, please, you please do this with me because I might make a mistake. And that will be on you people then. 7.35 times 10 raised to power 22 divided by 1.74 times 10 power 6. So this is 281750 joules per kg. Now to find the gravitational potential energy required to, that would be potential is basically, sorry, work done will be equal to change in potential times the mass. Change in potential will be 281750 times the mass of the rock is 0.50. And obviously, you're going to multiply that 4.50. And this is going to be 1.2627, I believe, times 10 raised to power 1, 2, 3, 4, 5, 6, 7. 7 joules. And I think that's what they needed. Okay, Sean. Do you guys understand this? Very simple, right? Any person who still thinks they need Zainab? Zainab, do I know you? No, I don't know Zainab. Okay. Now, the escape speed of the rock is minimum speed that the rock must be given when the moon surface can escape, right? Now, on this, at this part, you need to understand we have the work done. So we can use work done to, send something, you have to give kinetic energy to, right? So we have to find V scale square, right? Like that. So work done, we have already found, and half the mass of moon. Now this time I'm including mass because we have included in the other one as well. And V escape whole square. So now let's check if we could get the answer. We're going to multiply this value by 2, and then we're going to divide by 4.5, and then we're going to take under root of the answer. So from the moon, we just need about 2.4 of moon is basically 2.4 times 10 raised to 3. So in case you have a fight with somebody on the moon, so now you also know what to do. Okay, is that clear? Anush, Javeria?
Yes, sir, it is.
Okay. You have to be prepared. You never know when you need the right information. That's fine.
Sir,
Hmm.
Yeah,
I
thank
like
you.
the
Highly
idea
appreciated.
how, like, sir, I
Hmm.
like the idea how you're giving us hints on how to execute, but like, where do we get that much of
Okay.
speed from?
Physics means the science of all physical things, which means obviously you can apply them. It's not like chemistry, so it's okay.
Yeah, but
Then,
how do we send a person at that speed?
that's what you need to think about. Obviously, I can teach you certain things. So, some things are beyond even my scope. So I can teach you, because I've done civil engineering, I can teach you things about civil engineering, but not mechanical engineering. So what you're asking me to build a canal or something, probably I can't help you with that. You have to, be friends with some mechanical engineer then. So October, November 1342. Wait a second. So this is the answer. Let me just check the answer. I'm not sure about that. Can you please go? Let's see what you get. October, November. What was that? Can you please tell me? 13, 4, 2, I wrote, probably.
Yeah, yeah, yeah.
Okay, let's check the answer because I'm a bit unsure about that. So
So it's
this is,
correct.
it's correct? Wow,
Yes.
that's very good. Okay, saves us time. So now let's move to the next question. In the next question, they say the moon in B is assumed to be isolated in space. The moon does in fact orbit Earth. State and explain whether the minimum speed of the rock to reach the Earth from the surface of moon is different from the escape speed calculated in B. Oh, I don't think I think it should be different. Don't you think so? The reason why it should be different, because one thing is certain, that if you send something from the moon towards Earth, right? Not only the work you've done helps the rock to, do work against the gravity of moon, but also Earth is also going to attract it, which means that you would need less energy. Do you guys agree?
Oh, yeah, that
So,
makes sense.
So are
yeah,
you saying it's going to be the same?
no, it's going to be lower because,
It's gonna be lower then.
yeah, because one, you have done work. You have done work by applying force, right? Yourself. That
Hmm.
work that work needs to overcome the field of the moon, right? But also, you need to do less work because some of the work is done by Earth itself, because Earth will also pull the object. So Earth is kind of helping you. Do you understand?
But isn't the pull of the Earth very minor when it's near the moon? And isn't the escape speed only used to like get an object out of a out of another object's like field?
No.
Or am I wrong?
If you realize this, Munir, between Earth and Moon, there is going to be a null point, right?
Yeah.
So as the object thrown reaches null point, so that is the amount of work you need to do, right?
Yeah.
Beyond the null point, the Earth gravitational field will be in, greater than a Moon's. So
Yes.
it will kind of help you pull it.
Yeah, I get that, but like I'm saying, the speed which we just calculated, we escape 2.5, 2.4, sorry.
No. It
So
will be less.
isn't that, no, I'm saying, isn't that speed used to get the object from out of the moon's field to the null point?
No, that is to the infinity. Null point
Okay, so you're
means that,
saying if I'm like at the moon and I throw an object with that speed, it's gonna reach infinity.
yes, it will never come back to Moon again. That's
Yeah,
what
but
I mean.
where will it go? It will go towards the Earth, right?
It
Or in
will
the opposite
be
direction?
in some other universe,
Hmm?
maybe get impacted by any other object.
Oh, okay. Okay, fair enough.
All these things, like, you see, what you're saying is practically like sending something to infinity is impossible. The reason is because obviously, if you throw something out of Moon or Earth, there are bigger planets and bigger suns and other things which will attract it. So it can never truly escape anything. Do you understand? So
Yeah,
when we
yeah.
say infinity, we consider that that particular mass is isolated. There's no other forces. That's when we look at this. Okay.
Okay, sir.
Do you understand?
Sir,
Yeah.
Yeah, yeah.
Yes.
Yeah. Thank you.
sir, I have
Yes.
a little bit of a question.
Okay.
Would it be correct to assume, for example, after the object moves forward from the null point, it's going to be attracted by the Earth, right? So that just makes it lower. Is it correct to assume?
Um, no, not entirely. After
So
null
what
point,
what do you mean?
after null point, there's going to be a greater effect of how Earth is pulling it because the gravitation field strength is increasing, right? But
Exactly.
but if we say there is no force of Earth on the moon, that would be entirely wrong. In fact, there's a lot of force of moon on Earth because that is the reason why tides form, right?
Oh, yeah,
If moon,
waves and tides.
yeah, so if moon had no effect on Earth or the force does not reach beyond null point, then how would tides form? Do you understand? So the
Exactly.
thing is that there is going to be effect, and if you throw it from moon to Earth, from the very point that you're throwing, it will start helping you. Do you understand? So this
It
is the
will,
reason
yeah.
you need to do less work, and if you need to do less work, so you need to give it less kinetic energy to reach Earth, right?
Right, sir.
Yes. So then we can definitely say that the escape speed will be much lower as Earth would also attract attract the object. All right, is that clear? Like this. Okay, now, and if the question was that we throw an object away from from the moon, but it's going away from Earth, then we would say that we even require a higher speed than this because moon will, Earth will also have an effect to pull it back. Do you understand? Like that. So that's an opposite thing to, see. Okay. Now, so we're gonna come back to these questions. For some reason, I made a mistake by putting them
Sir,
here.
could you repeat that very last point you said? The point that you said it's going to move away and so the speed's going to be faster?
The speed needed would be higher, because if you throw
Needed
something,
would be higher, yeah. Yeah, needed
yeah,
would be higher, yeah.
away from Earth and Moon, then obviously both are going to attract it.
Exactly,
That
yeah.
okay. So that's something that I just wanted to put forward. Now I'm going to come back to these questions again, but yeah, I just want to start with the derivations of kinetic energy and the potential energy. This derivation of kinetic energy is a bit tricky. Potential energy, we're going to do GPE first, which is easier. So the gravitational potential energy definition derivation, simple. You say that E is equal to the change in potential times the mass. We already know that the change in potential is going to be minus gm over r times m. So no matter what, then you can obviously, this will be minus gmm over r. So this is as simple as this. But when it comes to kinetic energy, this is a bit tricky. Let's see. First of all, you're going to say that kinetic energy is given by half mv squared, and v is related to r omega like this, right? So what you're going to do is you're going to put it right into this equation. And if you do that, then kinetic energy will be equal to half m r omega whole square. Now you can open up the whole thing. It will be half m r squared omega square, right? Like that. Would you people mind if I write it as half times r times m r omega square? Would it matter if I write it like this?
Yeah, because you put force in it, so now it's going to be make it easier.
Yeah, I just separated like one r from the other, and I got this. If you look at this part only, you realize that this is centripetal force, which is mr omega squared. So can I replace this whole thing with half times r times centripetal force then? Fahad, very late, very bad. Okay, Saman, very bad. Okay, now, then we also know that since the centripetal force is provided by the gravitational force, all right, so this is centripetal, you got to remember that, is gravitational force, then what I can do is I can replace the same equation by half times r times gmm over r squared. Now, keeping that in mind, then I get to cancel this out, like one r from another. So kinetic energy then will be equal to gmm over 2r. And this derivation is very, very important. Okay, much more important than the gravitational one. I hope that's clear, everyone. Please have a look at it and let me know if you have a question. Nadia, Ahmed, Radhika.
So for GPE, what does the negative sign signify?
That gravitational potential energy is basically if you go away from Earth, right? So the change will be positive, and if you come towards Earth, it is going to be negative. Okay.
So
Negative
do we
sign.
use it in the calculation?
Yes, of course you do use it.
Okay.
It depends. It depends if it's falling or it's basically going away. So it depends.
Okay, sir. So if it's falling towards it, we use it.
Yeah, it will automatically be negative. And if you go to away from Earth, it will automatically be positive. So
All right.
like that. But generally, even if you ignore it, doesn't matter because change is going to be the same. Negative only shows the direction. Okay. Now,
Okay.
so in this next question, they have said that the mass of
Sir, like, I sorry to interrupt. Like in the
Yes.
last step, you're saying like half into R, then like it became 2R. Like, can you explain how?
If you look at this, Satish, this R and this square cancels out. So 2 into R is 2R and GMM is just there. You see?
Okay. Yes, sir.
All right. Now, the same question came. I don't know which year is this. Did I copy the year? 2015. And now they have asked the same thing. They have given you, let's show that kinetic energy of the equation given by expression. Now, this question I'm going to give you for homework because I have already, solved this. So you should do that. But, and the same thing, like I'm giving some questions from this as homework, not all of this. So I want you to do this part as homework, basically. So basically, this is the derivation, and they just want you to state the equation for gravitational potential here. Okay, energy. Then it says using your answer from I, derive an expression for total energy. Now, this is an important question. So we already know that total energy of anything is equal to the gravitational potential energy plus the kinetic energy. The gravitational potential energy will be minus GMM over R, and the kinetic energy will be GMM over 2R. And then you can just, subtract these. Can we subtract it? I don't think we can, right? We can take the reciprocal. If you want to, you can write it like this if you want. And you can also, take the reciprocal. So if you do that, this is going to be minus 2 GMM, and that's going to be plus GMM. And now it's going to be minus GMM over 2R. So this should be the expression. Do you guys understand this? Like that. Now, if you still have any issues, like if you think that okay, this is difficult, what you can do is to make it simpler is that you can make GMM as the subject of the equation. I mean, you can take it common. So it is going to be minus 1 upon R plus 1 upon 2R. And then you can take the reciprocal. If you take the reciprocal now, it's going to be 2R, and then it's going to be minus 2. This is going to be just 1. And then it's going to be GMM and minus 1 upon 2R. And then when you multiply, you get the same expression. Do you understand? If you want, you can do that too. That's the only when you have bad maths, like I have. Okay, like that. Now,
Sir, you have bad maths?
okay, a little bit. Now, small resistive forces acting on the satellite cause the radius of Earth to change. Use your answers to state the satellite whether each of the following quantity increase
Sir,
or
if you're
decrease.
bad, what about us?
No, you guys have your guys. You guys are good. You guys
Oh
are
my
good.
lord.
You will do better. So now check this out. This is something very, very important. So I need full focus here. It says small resistive forces acting on the satellite causes the radius of the circular orbit to change. Use your answers in A to state for satellite whether each of the following quantities increases, decreases, or whatever, right? So first of all, it says that what happens to the total energy. Now, I just want to tell you that if for the satellite, if they are resistive forces, so energy needs to do some work to overcome them, which means the overall energy, some of it is going to be dissipated. So overall total energy is going to decrease. Do you guys understand this? Okay.
Yes,
Now,
sir.
if the total energy decreases, right, which means that the object which was right here would also basically, now if the total energy decreases, it will not move at the same speed, so it will come closer to Earth as well. Do you guys agree? Why does it come closer to Earth? Because you see, the total energy basically is sort of like, you know, you need to understand that it's basically the resistive forces are causing it to slow down. And if it slows down, obviously the kind the basically what happens is, no, it doesn't like slow down. What I'm saying is that it comes down from that point, because the fact is that now it the force to make it move like this depends on F equals to mr omega square, right? Now, so you should understand the mass is the same. Okay, and now because the resultant force is smaller than before because there's a resistive force, then the radius would also be smaller. Do you understand? The omega is the same, which means the radius is going to decrease as well. Do you understand this?
So can you please repeat?
Yes, again, think about it this way, Gautika.
So even the first part, I don't get it.
Okay, why the total energy decreases?
Yeah.
Okay, so first of all, it says small resistive forces acting on the satellite cause the radius of a circular orbit to change. Okay. Why? Because now, if there is a resistive force, don't you think the energy of the orbit or energy of the satellite is going to be doing some work to overcome them?
Yes, sir.
So, don't you think the system would lose some energy in form of heat, probably?
Right.
Right. So if some of the energy is converted to heat, the rest of the energy is the total energy, right? That is left. So would it increase or decrease? What do you say?
Decrease.
Decrease. Okay, so is this clear now?
Yes, sir.
All right. Then it says if the total energy is decreasing, what would happen like to the radius? Would it increase or decrease? Now think about it this way. The object is rotating at a certain speed, right? Radhika.
Yes, sir.
So it will keep on rotating. But the thing is that now, because it has less energy, so it needs to rotate at a smaller radius. Why? Because if you look at the centripetal force requirement, it's basically depending on the mass of the object, the radius of the object, and the angular speed. Do you understand? Now, if the force requirement is the same, all right, I mean, if the force that is required, now you don't have that much energy to keep up with it, so your overall force is going to reduce, all right, which means that the mass isn't changing, the speed isn't changing. What is going to change then? The radius. Don't you think so?
Yes, sir.
If the radius changes, if the force requirement is now low, so the radius will also decrease. That's why I wrote decrease here. That's fine.
Got it, sir.
Okay, now think about it. If the satellite comes closer to Earth, would it gain potential energy or would it lose potential energy? That's my question.
Lose potential energy.
Lose.
So it means that the potential energy is going to decrease as well. All right. Now, the last thing that I want to discuss is, and that is very important actually, and that is what will happen to the kinetic energy? Hmm.
So the
Increase.
kinetic energy will increase.
Increase, exactly. The kinetic energy is going to increase because the kinetic energy, if the radius reduces, obviously the kinetic energy is going to increase because now it will have a smaller, like you can say, you can basically use mv square over r, or think that if you're losing gravitational potential energy, so you're now falling down, which means your kinetic energy overall is going to increase. Do you guys understand now? So you're losing potential, kinetic energy is going to increase, like that. So this question is very important because it causes you to think. Because if one of them you get wrong, then obviously you lose 4 marks. So please don't, just look at it. Let me know if you have a question here. All right. So now, while you're thinking, I'm just giving you this as homework. So you need to complete this. This is also a derivation question that came, and obviously they're going to help you, understand better from the perspective as well. All right. So change in potential and blah blah blah. Now moving on to basically the last part where we need to cover this particular formula where we started off here. Okay. Now, in this thing, if you see there is a planet and a stone is rotating about this planet at a speed v, as you can see. And then here you have this formula given. Now it says, Vijis, explain your working, you need to show the speed. So I would like to tell you is that sometimes what I do is when I'm confused about what to do with this equation, so I go backwards. Like I know that if I square on both sides, what do you guys see? V square and GM over R. Do you guys see that? Right? Now, check this part. Either this is related to kinetic energy, but there's V square. But then if I multiply half on this side and mass on this side, also half on this side and mass on this side, it does get me the kinetic energy equation. But the problem is that what to do with the half? So it is not related to that. Then I think about something else. I'll think, okay, if this is V and this is Gm, this part could be the force of gravity, this part could be the force of centripetal, right? So if I write it this way, mv square over r, and then gmm over r square, would you guys mind? So then it's pretty simple. This cancels out, and then this will go from v square equals to this r, and the square cancels out. So gm over r, and then you can take under root. And for 2 marks, this is a very simple derivation. Do you guys understand this?
Sir, could you repeat?
Again, you see what I did was I thought about it in a bit. I thought this looks like the equation that we just did for escape velocity, right? But this isn't. Why? Because if I square this on both sides, this is going to be v squared gm over r. Okay, Munib? Osman? Sorry, Osman.
Yes, sir.
Now think about it. If this was kinetic energy on this side, the kinetic energy will be half times m times v squared, right? So if I multiply this to make it kinetic energy, I also need to multiply this on the other side. What do you say?
Yes, sir.
The problem with this is then if you see there is no half in this equation, which means that this probably isn't related to kinetic energy. Understood? Then I think, okay, if this is v squared, then I also know in one of the formulas of centripetal force, it is mv squared over r. So I'm going to take it from there. So I took Fc equals to Fg. The force of centripetal is mv squared over r. Fg is gmm over r square. Okay, Suman?
Yes, sir.
So then check this out. This m cancels with m. This r cancels with the square. Do you agree? What are you left with? V squared equals to gm over r only. And then when you take the root, you get v equals to gm over r under root. And that's what we needed to prove, right? Is that clear?
Yes, sir. Thank you.
Okay. So this is how you should be also thinking. Anyway, now it says a second stone initially at infinity travel towards the planet, and the stone does not hit the surface of the planet. Determine in terms of gravitational constant m of the planet the speed v naught of the stone at a distance x from the center planet. Explain your working. You may assume that the gravitational attraction of the stone is due only to the planet. Okay, so it means it's isolated. Interesting. So what you're going to do now, if you look at the distance, right, from here, right? So it is this much of a distance, and that is the speed it is going at, right? Now we need to find that speed. So check this. First of all, we are going to take the equation on top. So we know that V is given by under root gm over r. What do you guys say? Right? Okay, speaking of this V then, and due to this attraction, we are saying that, okay, so then can I say the distance r is equal to x in this? Do you guys have any issues with that?
No, sir. No.
No, sir.
Okay, so if I could say this, then I would say that V naught has to be equal to somehow like something like, gm over x. But the problem is that it says only you need to give in terms of g and m. We don't want x in this. Or we do want x in this. We don't want x in this. No, no, no. We don't want. Sorry. This is not related to this. Basically, it says it comes from infinity. Fine. So it means if the stone was thrown from infinity towards this planet, okay, somehow, so it's basically losing gravitational potential energy, and it is gaining an equal amount of kinetic energy. Now let's try and do this, okay? So when it's losing gravitational potential energy, we are saying it's going to be change in gravitational potential times the mass equals to half times m v naught square. Can I write it like this then? What do you guys say?
Maybe yes.
Yes.
All right. So this change in potential at infinity will be 0 minus near this point. It is going to be minus gm over x. Can I write it like this, please? Times m equals to half m times v naught square. So this m and this m cancels out. This becomes gmx equals to half times v naught square. So this is going to be 2gm over x under root equals to v naught. And this should be the correct answer, I believe. So this is basically the same thing. What he has done is he has done the anti escape velocity. So this is the velocity at which it will have at this particular point. If there was r in it, which was the radius, then it would become escape velocity actually. Do you guys understand this? Like that. Please have a look at it and let me know if you understand this.
So what was the difference with R?
R would be if we had used R, then the equation would be 2gm over r under root. And that's the basically the escape velocity that's we derived here. Do you see?
Okay.
R is the radius, and this is basically at certain distance. That's why. Okay. Okay. The next thing it's asking us, which is very, very important, it says use your answer in I and the expression in A to explain whether this stone could enter a circular orbit about a planet. Can we go back? Where is I? AI. Use your answer in I. Where is I? Okay. And A. All right. So it says, can it enter the orbit that is here? That's the question. Okay. So now we have two equations. We have one equation as 2gm over x under root. And the other equation is, which is equal to v naught. And v is equal to um, gm over r. Okay. All right. Sorry, gm over r. Okay, r is the orbit. Okay, who can guess this, please? This is very important. You should see the difference between these two. So it's saying, let me explain this. It's saying at this velocity v naught, can it go into the radius at this point? That is what it's saying. Yes. Now think about it. Which means this is the same thing as, x is the same thing as r. Now, think about it, please.
Sir, V
Sir,
naught
but how
would be
will it
greater
orbit
than
in
V,
like
right?
That's the question. That's the question you're answering already. Go on. Go answer this. What is the difference between these two equations? If we say that at this point, x is equal to r, what is the difference between these two equations? Can I replace it? Can I write v naught like this and vs this? Yes. Can you guess the difference?
Sir, V
Which is
naught
going to
would
be?
be
It's just
greater.
the 2gm.
Yes. So it means that v naught is going to be greater. Do you guys understand this?
Yeah.
If v naught is greater, and the requirement for basically the maximum velocity that is needed for the stone to orbit in this particular orbit is v, then would it orbit?
No.
No, that is the very good question. That is the answer. So we are saying if we consider, right, x equals to r, then since v naught is greater than v, because it has 2 in it, it has no 2. So now it means the stone, so the stone cannot orbit. It might orbit some other point, but not at this point. Understood?
yes, sir.
So this is just, trying to give you like the perspective of these questions. There's sometimes very, very tricky questions like these, right? And the one that we did earlier. So now you guys need to do this as a homework. This is a very similar question. And also, yeah, and that's all. So I've given you like 2-3 questions. Now gravitation is complete, thank God. Okay, 60 pages worksheet. Now, but that's not for you. You need to submit this by the end of this week. So Friday would be okay, right?
Sir,
So I'm putting
60
a,
was for
Sir,
oscillations.
Saturday.
this is not 60.
No.
How long is it? Okay.
I think 15 or 16.
Really?
Yeah.
Oscillations? Okay. All right. Okay, I'll just put it on Saturday then. Chalo, theek hai, Saturday is fine.
Saturday, yes, sir.
Okay, gravitation. Uh,
Sir, Sunday, please.
no, Sunday is too
Sir,
late.
please.
Why? Why Sunday? Sunday, people have. Okay, let's not ruin your weekend. You're right. Let's do it Sunday. Sunday,
Thank you.
done. Sunday is the due date for this. Please upload the PDF completed, and you will receive your circular motion by Friday, inshallah. All right. See you then. Have a nice
Sir, what
day.
about the notes? Like last time you sent the whole PDF of completed whatever you wrote.
I said this is the last time doing this because you should be writing in the same PDF that I shared in your own words.
Oh, okay. Don't
Yeah,
worry, I'm
yeah.
just asking.
Okay, it's all right. So, see you people.
Sir, where do we get this PDF?
Who's asking this, first of all? Ahmed. Ahmed, is that you?
Sir Fahar.
Fahar. Okay.
Sir, because when I opened the Google Classroom, I couldn't find the assignment attached. I could only see that there was this this assignment assigned,
Assignment.
but I couldn't
No,
find
no,
it.
no. Okay, I'm moving this link to top. Somehow this application must have a pin to it. You see this link? 9 January wala. You see this? Far? You click it, please. You click it. You go to the drive, right?
Okay.
You will find this PDF here. And also the next one that you need to print on Monday, like before Monday, the oscillation one. Okay, this is here. Okay, Gatika is 26 pages, not small one. That's fine. Okay. All right. So see you then. Have a nice day. Bye.
So
All right,
yes,
sir.
sir.
today's
You too. Bye.
lecture